Is it working fine? Can you hear me? Or so I would like to thank the organizers for inviting me. That's an honor for me. I didn't have many invited talks by now. It's a great place to be. Also, I will talk to you about photon correlations as a tool to improve imaging. Okay, so since I will use old papers by Leonard Mandel, I think the title for my talk could as well be Photon Correlations Brand New Second Hand, which happens to be the title of a CD of my favorite British musician, Lutz Manuwa. So I really recommend this CD to you. Okay, the best track is Witness the Fitness, if you want only one. Okay, so these are the second-hand things I will use in my talk. 3 papers by Leonard Mandel and his group. And since, okay, the first one is about inducing coherence by aligning beams, a bit like in Masha's talk. The second one is showing interference of independent laser beams. So like non-orthodox interference. You would read in optics textbooks that for light to interfere you need the light beams that interfere to be coherent. So if you take 2 laser pointers and shine them on the wall, you don't expect to see fringes. But actually Mandel in this paper in 1967 showed that that's not true. You can see fringes from 2 laser pointers if you look carefully. And the third paper is photon anti-bunching, also by Mandel. And since you cannot be paid only for reading old papers, I would really enjoy such a job, but you need to write something in your grant proposal. So we were able to produce some new results with these old papers. So this one we applied to imaging. This to interferometry in the presence of phase fluctuations, and the third one, unfortunately it wasn't. I wasn't a part of this research. It was done in Jaron Silverberg group. He showed that anti-bunching can be used to improve microscopy. Okay, so let's start with the first part, induced coherence. This part of research was done when I was a postdoc in Anton Zainger's group. The main person in this experiment was Gabi Barreto-Lemos. Okay, so I start with even older stuff and more basic. And we opened the textbook of Feynman on quantum physics. He explains interference. So if you have quantum particles and they have 2 ways, they have 2 ways of reaching the detector, you expect interference fringes. And then you might start wondering, what if we somehow sense which way the particle actually went, right? And then Feynman goes on to explain that the fringes disappear as soon as you do this. And he states this fact as a general principle, that you have interference fringes only if you're not able, or if there's no possibility to distinguish the alternative possibilities that could lead to detection, right? So only you can see these fringes if there's no way of telling which way the particle took. If there is a way of telling which way the particle took, the fringes disappear. Okay? So this effect was the basis of a paper by Mandel. And okay, another ingredient apart from Feynman's this principle is the process of parametric down conversion that I think most people here are familiar with. So you pump a nonlinear crystal with a laser, and you generate photon pairs. So the important fact for this talk is just that you can generate pairs of photons. So always these 2 guys always come in pairs, and they have to fulfill the conservation principles. The momentum conservation is called phase matching. Energy conservation is also there, but we will use only momentum conservation, which leads to spatial correlations, entanglement, and the fact that they come in pairs. So now we can take 2 such sources of correlated photon pairs and build an interferometer. Right. So this is to prepare these two alternatives that could interfere. One alternative is a pair produced in the upper crystal. One alternative is a pair produced here. And then we might start wondering if the two blue beams would interfere in this case. So who thinks they would interfere? Hands up. Okay. So actually they wouldn't in this case because the red beams are misaligned, right? And since okay, maybe you didn't look carefully at it. So the two alternatives wouldn't interfere because you could always detect the red beam, and since the red beam is different for the two crystals, there would be a way of telling from where the blue photon comes. Okay. So to make the pairs interfere, I think many of you know the solution. What you have to do, you need to align the beams, right? So you need to get rid of this information, so you make sure that this beam is the same as this one. Okay. This was done in a paper by Mandel, in this one. So here this is this red beam, and it's the same for the two crystals. So it doesn't help you if you have a detector here. You cannot tell if this red photon comes from this crystal or that crystal. And this is why the blue photon coming from this crystal and from the second crystal can interfere, and you can see interference fringes at this detector. One important point about this paper is that it's good to actually read it, not just look at the figure and title and maybe graphs with fringes, because all quantum optics experiments show some kinds of fringes. And you may think that this is just another entanglement paper, but it's not. Here the coincidence logic is actually not useful. It was used for technical purposes, it's not used in the actual measurement. Okay, so the point is that these fringes here really appear in intensities, in photon counts, not in coincidences. So I think Mandel wasn't that great in selling his results, drawing this big coincidence box here. Okay. So this is Mandel's results, showing that if you now block this beam here, you kill the fringes at the blue beam. If you keep the beams aligned and you don't have absorption here, you see interference fringes. And the visibility of the fringes is proportional to the transmission between the two crystals. Okay. So what we did in our experiment is we took the Mandel setup, we added spatial correlations or entanglement and imaging systems. This is what you get. I maybe skip the technical details. If you want to talk about it, we can talk after at the coffee break. So yes, we make sure that photons generated from these crystals are spatially entangled. And we image this crystal onto that one, like in Masha's talk. And we image this plane onto the camera. So this allows us to like repeat Mandel experiments with many pixels. Right? If we now decide not to entirely block or unblock this beam, we can do it pixel by pixel. And at the corresponding pixels on the camera, we will see high or low visibility. So it's just like many Mandel experiments in parallel, thanks to spatial entanglement. These are results for a simple object, which is just blocking or unblocking the beam. You can see at the output of the interferometer, you get the object. Since it's an interferometer, you can use it for phase imaging. This is a phase object which we etched in silicon, just to demonstrate that you could have an object that you want to sense at, let's say, 1550 nanometers, where you don't have great single photon cameras, and you want to see the image at a good camera that's available at 810 the object was opaque at 810. Anyways, we can do face imaging. Okay, so we use this effect to, knowing the state that we prepare to image objects that we don't know. You could reverse the logic. You could place here between the crystals an object that you know and hope to characterize the correlations of light emitted from the crystals, right? Because in order for this imaging to work, you need correlation between pixels for the idler beam and for the signal beam. So we did this experiment too. We placed an object which corresponds to a quadratic face in this plane and observed interference fringes. This is for the best spatial correlation that we could generate. This is for the weakest correlation we could generate. We are tuning the level of correlation by tuning the bump width. You can calculate, knowing the theory of this process of parametric down conversion, what correlation width you expect when you change the pump waist. This is the blue curve. And then from the theory of my colleague, Radek Lapkiewicz, we could calculate from these different visibilities of interference fringes that we observed, we could calculate the correlation that we expect. So this is a method, at least in this setting, that we can quantify the correlation by measuring, so correlation between the two beams by only measuring one of them. Of course, the price to pay is that we measure it in this funny setup where we need two copies of the source we want to characterize. So there's no magic here. Still, it's could be a useful technique if you don't have a way to detect this beam at all. So please do ask questions if you have them. I think it's better if we discuss already now.
I do. Yeah. So the red dotted line, is there a mirror missing?
Yeah, so there's a dichroic mirror here and here.
Yeah.
Okay. So this was work done in Vienna and done in collaboration with the group in Vienna. Then I moved to Warsaw 2 years ago, and these are the people I work with. So these guys here, well, the 5 guys are undergraduate students, but I really need to stress that they are really super bright, greatest students in the world. I'm really happy because last week my first PhD student joined the group, so yes. And I have more PhD positions available, so please talk to me at the coffee break if you want to join us. Okay, so anyways, this is the group. And we took, of course, another old paper by Mandel, just as Anton Zeiger taught me. And so this was first this paper about interfering, two laser pointers, two independent laser pointers. And the second one, if you want to repeat this experiment at the very low light level. This is the setup for the first experiment. So I cheated a bit saying that these are independent laser pointers. Actually, the frequency difference of them is monitored, and the measurement is done when the spectra are close enough. But I think it could be done in a technically different way with really two independent lasers. We just need to make sure that their spectra overlap. So, although there were no intensified cameras at this point, Mandel still was able to build his own device, which allowed him to have very short exposure times, sub-microsecond. Yeah, it's really sad that in the 60s already, having no equipment, he could do stuff that's like, I don't know, it's hard to reach right now. Anyways, so the trick to observe the interference fringes that he did over here. So this stuff here, if you integrate in one direction and cut through it, you get these nice fringes. They appear here. This is a tube which takes photons. There's a photoelectric effect here. You accelerate them in electric field, and you have a phosphor screen like on an old oscilloscope and you take photos of this phosphor screening with regular camera. What's important about this tube in this particular experiment is that it allowed Mandel to take very short exposure times, sub-microsecond, thanks to gating the voltage on the tube. Okay, so what he has shown is basically that if you don't see interference fringes from two laser pointers, it's because you're not looking fast enough, right? There are fringes at each coherence time, but they're just jumping from position to position. And you usually integrate over these different positions, so you don't see the fringes. Then he did a similar experiment with lower light level. Here he needed to assume the shape of fringes and then prepare a special device to sort the fringes into two detectors. It's a bit tricky, this thing. Anyways, the presence of fringes appeared here as an anti-correlation between the two detectors. Okay, so we now have a better camera than this one here. Our camera is based on an image intensifier, which was developed not for quantum optics purposes. It also is based on photoelectric effect. So the electron is kicked out, then it reaches one of these holes in a microchannel plate that's placed here. This is a microchannel plate. Electron is multiplied, so we get a photon, one electron, 100,000 electrons, and then million photons. One photon to million photons. Of course, they are not coherent, right, with this photon. They have different wavelength. It's just a way of measuring light, and then you need to add a camera to construct a single photon sensitive camera from this. So this is the design that we used in our lab. It was developed by my colleague Wojtek Wasilewski, and now the camera is also available commercially. I mean, the companies developed it as well. This is our home-built version. So the nice thing is that it can be gated with gating time around 1 or 5 nanoseconds. It's single photon sensitive. There's basically no noise if you operate it at very short exposure times. A benefit that you get for free from this camera is that you have resolution of photo detection not limited by your CMOS or CCD sensor. You can localize the photon events with sub-pixel resolution because you have a lot of light for each detected photon. And this is what our device does. The biggest limitation, because I'm not a salesman, is the rate of the frame rate you can reach on your CMOS sensor. So this sounds great, 1 or 5 nanoseconds, but you can only get this precision if you open your gate of the image intensifier once per frame. If you open it many times, your CCD or CMOS sensor integrates all of them, and you don't know which was when. Right? So this is not yet achieved. Otherwise, this would be a perfect solution. Okay. So we didn't use Mandel's idea to interfere to lasers. We thought of an interferometer where you have some spatial phase, which could be a biological object that you want to characterize, and you have some instabilities, which I represent here as temporal phase. So this theta of t varies quickly with time. And you could fight against fluctuations by simply taking very short exposure times, but this is getting impractical if the fluctuations are fast and if you don't want to burn your sample. So if you limit the light intensity and you have quick fluctuations, you end up with not too many photons per time when the interferometer is stable. I don't know if it's practical. Anyways, our method would be useful in such a scenario. So this is what happens if your phase is fluctuating. Okay. If you add many shifted fringes, of course, you could just get your beam profile. So we don't do this measurement. We instead have a camera that's single photon sensitive, and we record positions of photons detected at each output. And we do this only in one dimension for simplicity and for speed. So position of photon detected at this output we call x. Position of photon detected at this output is x prime. And then we can plot such a histogram. this is x and x prime, and the color of this graph represents the probability of detection at this particular location, right? The two locations, this x and x prime corresponding. And this one is for fixed phase of the interferometer. And this is what happens if you add many such patterns for shifted phases. So the magic that happens is that these two photon patterns don't average to the beam profile. They still keep some modulation with lower visibility, but you get information about the phase. And so we went and done this experiment. These are experimental results, and for quadratic phase, and these are some quadratic phase and some other phases just for fun. We could measure them. We introduced the phases in the interferometer with a spatial light modulator, and I believe that these funny things over here are artifacts of the spatial light modulator. Okay, so the last part is another paper by Mandel, anti-bunching. So I don't know, just to be sure, I remind you what anti-bunching is. Imagine you have a single photon source here. If you generate a single photon, only one of these detectors can click. So if you record for certain time the count rates of the two detectors and compute these functions. So I wrote intensities, but this could be also numbers of photons detected at the two detectors. You can compute the so-called Gto function, and then when you plot it for a single photon source, you get a characteristic dip, meaning that one photon cannot click at the two detectors at the same time. So unfortunately, I wasn't the first one to try to use this experiment for imaging. The guys from the Weizmann Institute did it first. So they built an fluorescence microscope and acquired regular images, and then also images where they combine the information from intensity with information from G2 measurements. So they turn the camera into number resolving camera by combining groups of pixels. If you have a couple of pixels, you can count like 0, 1, 2 photons, right? And then they can measure like G2. The idea is that if you have 2 photons detected, you know that they had to come from 2 different emitters. And then knowing this, you can combine it with the intensity measurement and subtract this information to sharpen images. It's really a cool idea, but I'm not able to explain it in 2 minutes. So these are the guys that I'm very happy to collaborate with on this project. In case you're not fluent with Hebrew letters, it says Weizmann Institute here. And they really have such trees on their campus. It's a beautiful place. And yeah, I'm very happy to have a collaboration with Jaron Silverberg's and Dan Oren's groups. And we continue this project on using correlations in fluorescence microscopy. Another thing they demonstrated before I arrived was measuring the Gto function and getting the information about how many emitters sit in your blurred spot in microscopy, right? If you just see your smallest possible spot in your microscope, you cannot say how many emitters are there. But if you measure the Gto function, you can, because the G2 at 0 is given by this formula, 1 minus 1 over n, where n is the number of emitters. So they use this and combine with the ideas of localization microscopy. So recording the G2 as a function of time, they could like slice the time into pieces where different emitters blink, and they could post-select only on these parts where one emitter is active, and they could use this for localization, because this is a requirement for localization microscopy, that you only have one emitter active. Okay, so let me sum up. Using papers of Mandel, we demonstrated that you can image objects without detecting light scattered by them. This was the first experiment. When you reverse this, you can witness correlation between 2 photons by only detecting one of the photons. When you measure correlations instead of intensity, you can be immune to phase fluctuations. And measuring the Gto function allows you to do the impossible in fluorescence microscopy. Impossible if you just measure intensity. And here a small advertisement. If you're looking for a PhD or postdoc position, come talk to me. Thank you very much.
Thank you, Radek. Are there any questions?
Could you go back to the image? No, the bit after the image intensifier where you have that one. So what exactly are you measuring? Because you have your phase theta and phi are both fluctuating, right?
No, phi is fixed. So phi is supposed to be the sample, and then your interferometric setup fluctuates.
So this gives you your information about phi.
Yes.
Okay. Yeah, thank you.
Very.
About the same experiment, I didn't understand. The Mendel paper was just about not about coincidence counting, right? So
No, it actually was the second one. Sorry, I went through this really quickly. Yes, this one. So here, he needs to, compared to us, he needs to know what fringe pattern he expects. And the pattern jumps from shot to shot, and by doing this funny trick, you can detect the presence of interference.
John?
Yeah, I think this is just strangely enough, this is the Hom dip done with separate phase randomized sources,
Right.
where you see an anti-correlation because it's essentially when you put a random phase onto fields, then you get a sine function, and when you average the correlation between the two outputs, the prophetic multipliers, you see this suppression or anti-correlation between the outputs, which goes to 50% visibility rather than the 100% of the
Right.
omnip. So I think that interferometer is effectively giving you that anti-correlation.
Right, that's true. Thank you.
We have time for one more question.
So in the initial experiment, you're looking at imaging the sample. You were able to make the idler beams from each crystal have a fixed phase reference, so they'd interfere. To what extent could you achieve that by seeding both crystals with a common seed in the signal mode?
I think I didn't get the question.
So here you pass the signal from the first crystal into the second, which fixes the phase of the idlers from each. To what extent could you do that by just using normal parametric amplification with a coherent beam in both the signal modes of the crystals?
Okay, so you mean a coherent beam going through the red path here? Like this? That going through?
Splitting before the first one and entering both crystals.
Yes, you could do this as well.
Yes.
And actually, Mendel did it as a first step to this experiment. The disadvantage of this approach is that you don't get spatial correlations so easily in this case. Because, right, you need to induce it with some, I don't know, thermal state or whatever, spatially incoherent state. If you just use a laser, like one Gaussian beam, then you would just have no correlations in the induced field. And the spontaneous thing is cool because it has all the possible modes that are not forbidden, and thanks to this we can image.